All right, so we demonstrated, the last little circuit we demonstrated to drive that motor was a FET, okay? And that's a type of transistor. It's one of many different flavors that we said there are. And it's like an electrically controlled switch is how we're using it. So you can see on this schematic representation of a MOSFET, we actually have a 3-terminal device, just like what we wired up on the
That's
breadboard.
right. So transistors are often more than 3 terminals, but really we're going to focus on the 3 important ones for this simple model. And in the case of this particular type of transistor, a MOSFET, the terminals are the gate right there, the drain, and the source. And I think you saw from what we just did that really the voltage on the gate is kind of acting to control something interesting going on between the drain and the source, right?
That makes sense. The gate is our control point.
Mm-hmm. And if you look at the symbol just as a matter of just sort of general interest, this is modeling in a symbolic way the fact that when you build these at the nanoscale, there's in fact a little insulator between the gate and the rest of the circuit. One other point, for those of you that may be looking at schematics, some schematics will have a circle around this, but doesn't really change much. And we'll get to one last variant that's important about MOSFETs, one last little modification that happens here in the symbol that means something in a minute. But let's go back to looking at this thing. So there's 3 terminals, right? Okay, so let's go back to looking at the basic FET. So we've got 3 terminals. And so we might be interested in the voltages and currents between those terminals, right?
Yeah, absolutely.
So what are some currents or voltages of interest that we're going to see again and again when dealing with FETs?
Well, there's definitely the voltage on the gate, between the gate and the source. So we call that VGS. That's sort of our control voltage, right? We can set voltages at the gate. We'd also be interested in the resulting current that flows from the drain to source, and also the voltage between the drain and the source, right?
Okay. So first thing to load into your heads is that it is the difference in voltage between the gate and the source, that voltage, which is going to control something going on between the drain and the source. Just get used to that. And then because this gate source voltage is changing something, what do we care about these 2 terminals? We care about the current and the voltage. That's kind of the way to look at it. Think about a box, as we were sort of looking at before. And if you have some arbitrary device whose voltage is V ds and whose current is I ds, right? We care about those 2 things because then we can build a model. What's the relationship between VDS and IDS, right? And the knob that allows us to change what's going on inside this box, that knob is this VGS voltage.
That's our gateway.
Okay, that's exactly what it is. All right, so let's look at what happens if we were to do this. If we were to take some curves of how IDS changes as a function of VDS. Right? It seems a reasonable thing to do. Let's just take some data. Oops, bad choice of scribbles. Well, what you see is a curve like this. And we've added some numbers just to give you some impression. These numbers will vary widely if the FET is intended for high power applications or if it's a tiny, tiny little FET inside your semiconductor chip. So here's VDS on X, here's IDS on Y, okay? And because we said we can change VGS, we actually get a different curve for different VGSs.
I see. So by setting VGS to a certain voltage, we get a different IDS versus VDS curve.
That's right.
We're controlling the IV characteristics of that box.
Exactly, of that box. And so for our model, if VGS is very, very low, you can assume that, let's say VGS is 0, you can assume nothing happens. Okay, you can in fact assume it's largely kind of like an open circuit. It's going to run 0 current between it no matter what voltage you put on. That's this red line, right? It's open if VGS is 0. What's going to happen is I increase VGS. For very small VGSs, there won't be much of a change, right? But then after I get beyond a certain point, then as I change VGSs, you'll see curves like this. So let's say I set VGS at 1 volt, right, on this mythical FET. For very low VDS, for 0 VDS, I'll get 0 current. They all intersect with 0. Kind of makes sense?
Yeah, you need a difference between D and S to get a current to flow.
Exactly. And so that'll come back in the way we use these things. But then as I increase that VDS, what I'll notice is I get this little bit of current that increases. Let's say here, sorry, I was on 1 volt, so here. So I get current increasing, but after a little bit, not at too high a voltage, it'll just kind of flatten out, pretty much flatten out. Not entirely, but pretty close to looking like a horizontal line.
Oh,
This region is called saturation. So it kind of makes sense. It's saturated out. You can't make it go any higher.
I see. The horizontal line is saturation, just one current
That's right.
outputs.
And if you're very close to zero, you kind of get something that looks like it could be a resistor, right? If you extrapolated a bunch of straight lines, right? Whoops. There we go.
So it's kind of linear for a while, and then it sort of makes its transition into the saturation.
Right. So around zero, it's linear. Once you get out to a large enough VDS that you've saturated it, that's what this VSAT means. Beyond this region, the curves are all horizontal. Now, they're horizontal, but they depend on VGS. So now let's simplify this. Let's say that we only really care about being more or less out in saturation. Yeah? And then now what I do is I ask myself, as I set out in saturation, as I set these voltages, what could I model this if device at? It's clearly not a linear device, right?
Right.
But maybe we can linearize it. Maybe we can pretend it's linear for a certain region. Let's ask ourselves, for the region to the right of this dashed line, could we replace this with something we know? Okay, so here's the curve, and I'm gonna suggest what we could do it.
All right.
How we could replace it. What if this thing was simply a current source?
Okay, so what's between DNS? It's just a current source?
Right, this is between DNS, right? Between DNS. Let's pretend there's just a current source whose value depends on some gain times the VGS voltage.
Okay, so we have VGS worked into our model. It's the control signal.
That's right. And what would that look like? If it was a current source, what would it look like on this plot?
Current source should just be a straight line, right? Constant current for any
right.
VDS.
It just gives you a current no matter what voltage you put across there. Pretty much like this. So this is the idealized, right, result or plot. And this is our simple linear model. Fair enough? Okay, so we can apply this right away. I've added a little R up here, by the way. This is not part of the model. We'll come back to this in a minute. This is not part of the model. This is sort of if I built it into a circuit. But what you can see, this is just so, by the way, so there's a complete, up to VDD connection. But what you can see is we've replaced this thing, which looks maybe scary, ooh, it's a transistor, with something that you already know how to do, which is just a current source that's controlled by a voltage. And notice there's no connection between this up here and anything else in the circuit. This sometimes bothers people, right? This little thing is sort of floating up there. There's no current going anywhere. Here it goes up to something, right? In our model, all we're doing is sort of measuring this voltage and then using it to do something else.
Well, that should look kind of familiar because we said something similar about ideal op amps, right?
That's right.
We said there's no current flowing into that terminal, so we can just call that a node that has a certain voltage on it that
That's
we're
right.
detecting.
It's like an ideal op amp in the sense that the input impedance kind of looking up here is sort of infinite, right?
Very high.
It's an open circuit. Okay, let's go use this. I think we can build just with this a single transistor amplifier pretty easy. But let me throw a couple of things at you for those of you that like thinking about these things. This model is very simple. And you can, I think if you spend a few minutes, you can imagine all sorts of things that would be added to this model to better really model what's going on. And one thing we're not talking about is transient, time-dependent kind of stuff. In other words, we're showing you these steady state curves. You might ask yourself, well, does that mean a transistor can switch infinitely fast? Is there any sort of interesting things that happen with time? And of course there are. And the reason there are is that embedded within a real transistor is not just something that maybe looks like this, but a lot of little capacitances that come with the structure of the transistor itself.
Well, and with capacitances, of course, we know we have RC time constants and charging, discharging times.
So one other thing I want to load into your head that we're not going to go in any detail in this class is that you can imagine that there's all sorts of little caps between these terminals that we're looking at, right? Between sort of DNS and even GNS and GND, there's these little capacitances. And you could draw them in your idealized circuit. And then when you go build an amplifier, you don't just have a simple resistor circuit, you have to do these RC calculations you're mentioning. And that will set, and you can, by the way, you can do the same type of phasor stuff we just finished doing in the last module. And so that'll set how fast things can go, what kind of filtering the transistor is effectively doing for you. It's going to cut off at too fast a frequency. These are all great topics if you like this stuff to go delve deeper.